Welcome back and a very good morning to all. If you recall back in our previous lecture, we dealt with formulation of scattering parameter, and last time we saw some of the important properties of scattering parameters. That time we discussed the importance of scattering parameters and why scattering parameters are used at high frequency analysis of the given circuit. Okay, and later on we went through the some of the important properties, and the last property which we studied that was a very important, and that property was the unitary property, which was again classified further into two different conditions, the zero property and unit property. So with the information and background of a scattering parameter, so we move ahead further, and we will see how to represent the different types of losses that may take place in a given microwave circuit when it is being operated at a very high frequency. Okay, and thereafterwards we will set up a theory in order to understand the usage of matching circuit. Okay, so today's lecture we will devote to understand the different types of losses and how these losses in the given microwave network are represented by means of scattering parameters, and thereafterwards we will develop a theory in order to understand the importance of designing impedance matching circuits. Okay, so let us go ahead. I already prepared the notes. So here, first of all, let us discuss what are the losses that may take place in a given microwave network. In the view of broad spectrum, the losses that can take place in a given microwave circuit are broadly classified into three types. The first type of loss is a transmission loss itself. The transmission loss is going to indicate the loss that will take place during the signal propagation from one point to another point or from source to load. So the first type of a loss is a transmission loss. The second type of a loss which we normally encounter in a microwave devices, that is a insertion. So insertion loss, the name itself indicates that whenever some third device is connected in between two devices, so there is a reduction in the signal amplitude. So this signal reduction is taking place because of the insertion of that third device into two devices. So that we'll see later on in detail the formulation. And the another type of loss which is very frequently encountered whenever the impedance matching is not perfect, that is a reflection loss, or sometimes it is also popularly known as a return loss. Okay, so on the similar base, whatever the transmission loss we discussed, the transmission loss is also known with the other name as a attenuation loss. So please remember, transmission loss is nothing but attenuation loss, and sometimes the reflection loss is also termed as a return loss. Now here you observe a two-port network. Okay, so please remember we are taking many times the example of a two-port network in order to illustrate the concept of microwave engineering. Okay, so the same two-port network I am taking again over here. Now what it has, again the same, there are two ports. Port 1 is we have treated as a input port, and port number 2 we treated as an output port, and I have shown the incident and reflected waves at these two ports. So A1 and A2 are the incident waves at port number 1 and at port number 2, and similarly B1 and B2 are the reflected waves at port number 1 and port number 2. Okay, so let us say at port number 1 we have connected certain source of a power. Actually this source is operating at microwave power, remember. So let us say Pi is the input power which we fed at the input port. Okay, and at the output port we get certain power at the output port, and that port power we denote with letter Po. Okay, so output power is denoted by Po, which is available at port number 2. Okay, now please remember, whatever input power that we feed, that is a Pi, not all of the power is being made available at the output. Okay, so this is where the losses are going to contribute. Okay, so why the total input power is not going to be available at the output? because there are certain losses that will taking place. Okay, so these losses that is taking place whenever we give the input, so these losses can be because of these three different types of losses. It could be transmission loss, it could be an insertion loss, or it could be happening because of the return loss, because of imperfect impedance matching. So let us see what happens. Okay, so the input power, whatever we feed, all of that power will not become available at the output. Okay, so when we feed certain input power, all of that input is not available at the output. That means certain power from the input side will get reflected back. That power we call it as a reflected power, and it is denoted over here PR. Okay, so here we consider three different power entities: input power represented by PI, output power represented by PO, and PR is the reflected power. Okay, so the reflected power will reduce the amount of power which has to be get delivered at the output port. Okay, so the same circuit I have drawn over here. This is the input power and this is the output power. Okay, so the two port network here, it is connected with a generator on the left hand side. The generator is also known as a source. Okay, and it is connected with the two port network by making use of a transmission line. Okay, so the network, so this could be representing any network, so this could be representing any circuit, microwave circuit, right? So this microwave circuit is connected on the left hand side to the generator or the source by making use of a transmission line. So let us write how to write the equation for insertion loss. So what we have over here is, this is actually a two-port network, right? So this two-port network is inserted inside the transmission line. On the left of this transmission line, here it is, I have written a generator. Okay, so the transmission line, so this one, on the left hand side we have connected a source, and on the right hand side somewhere there is a load. Okay, so in between generator and load I have inserted my network. So when I insert a microwave circuit inside a network, so it is going to cause certain insertion loss. So this insertion loss in terms of power quantity is given by this equation. So how the insertion loss is given? Insertion loss is equal to, we will take the ratio of powers and a logarithmic scale. Okay, so as we are going to deal with the power, we will take 10 log. So the equation of the insertion loss for this particular situation is equal to 10 log to the base 10 of input power divided by the output power, right? So where PI is the input power and PO is the output power. Now if we substitute the power in terms of wave representation, okay, so the input power, what is the input power? Say I will draw over here a two-port network. So this is your input port and this is your output port. So here we have A1 as an incident wave and B1 is a reflected wave, right? Similarly, this is at port number 1. At port number 2 we have A2 as an incident wave and B2 as a reflected wave, right? So how we represent the input power? Input power is represented by the incident wave. Okay, so in the numerator we will get A1. Okay, so what is the output power? Output power here is nothing but the reflected wave at port number 2, so that is B2. Okay, and they are squared because these incident and reflected waves are representing the voltage. So anyway we are dealing with the power, so that's why we are going to make square of the reflected and incident waves and take the logarithm scale. Okay, so if you take the ratio, so what you do is you take A1 in the denominator. So what I will get? 1 divided by B2 by A1 whole square. I can write the same equation like this. Okay, so what is B2 by A1? B2 by A1 is nothing but S21 from 1 to 2, right? So insertion loss is then finally given by, in terms of scattering parameter, with this equation, insertion loss IL, in short it is called as IL, standing for insertion loss. 10 log to the base 10 of 1 upon S21 whole square, where S21 is nothing but the transmission coefficient. Okay, so this is how we represent the insertion loss in terms of a wave representation, and the waves are representing either voltages or current. In order to convert them into power, we will take square of it, and we will represent that in terms of a power, and that can be represented back conveniently in the form of scattering parameter. Okay, so let us go ahead and see how the other two different types of losses are represented. Okay, so the next loss is a transmission loss. We know that transmission loss is the loss in the signal during its propagation. Okay, so it is nothing but the attenuation of the signal. So please remember, transmission loss is nothing but the attenuation. So how it is given in terms of a power? Again, please remember, we are going to deal with three different powers: input power, output power, and the reflected power. Okay, so how we can represent the loss or the attenuation in the signal whenever it goes from one place to another place? So it is written, which is given in this particular equation, 10 log to the base 10 of difference of input power minus the reflected power divided by the output power. Okay, so similarly, if you put the analogy, what is the input power, what is the reflected power, and what is the output power? So in terms of scattering parameter, the transmission line loss or the attenuation loss is given by scattering parameter equation 10 log to the base 10 of into bracket 1 minus S11 square divided by S21 square. Okay, so the way in which we converted the waves over here in the insertion loss to scattering parameter, on the similar line you can put these power entities in terms of waves and square them. Okay, so finally you will get this particular answer. Okay, so the transmission loss or the attenuation loss is dependent on S11 as well as transmission coefficient S21. Okay, and finally the last type of a loss that remains, that is the return loss. Sometimes it is also known as a reflection loss. And how it is given? In terms of again the three different power parameters: 10 log to the base 10 of input power divided by the difference of input power with reflected power, right? So it is given by this particular equation, right? So if you replace the power entities in terms of incident and reflected waves, and when you convert them into scattering parameters, the reflection loss or the return loss equation becomes 10 log to the base 10 of 1 upon 1 minus S11 square. Okay, so these are the three typical different types of losses that will normally gets encountered in the microwave operation. So first is the transmission loss, attenuation loss, second is the insertion loss, and third is a reflection loss or return loss. Okay, now let us go ahead, as we discussed and as we indicated during our beginning of the lecture. So after observing the different types of losses and formulating them in terms of a scattering parameter, let us go ahead and discuss the concept of usage of the impedance matching circuit. Okay, now in this next discussion, what our focus is on to understand why one requires to make use of impedance matching network in the design of microwave circuits. Okay, so for that purpose, let us consider this transmission line circuit diagram. Okay, so let us say a microwave circuit which consists of a generator on the left hand side. This is a microwave generator, please remember, operating at a microwave frequency. This generator has internal impedance. It is represented as a ZG over here, right? Now this generator is connected to the load on the right hand side. This is a load which is connected to the generator. Okay, and in order to connect the generator with the load, we are going to make use of a transmission line. So this entire microwave circuit can be divided into three sections. Okay, so the first section, which is there on my left hand side, that is the generator. The generator has a source of the signal, voltage source of the signal with internal impedance ZG. Okay, or we can call it as a input generator impedance. Okay, on the right hand side I have a load, complex load impedance, which is indicated as a ZL. Okay, so the generator and the load, they are connected by using a transmission line in between. So here you observe I have made three different sections. So first section is a generator, second section is a transmission line, and third section is the load. Now let us see the situation. Now the generator has the impedance, that is again a complex impedance. It is denoted by Zg. So Zg is the generator impedance. Similarly, a transmission line which is connecting the generator to the load side will have its own characteristic impedance. Okay, so we already defined what do we mean by characteristic impedance. So the impedance of a transmission line is denoted by Z0. So Z0 here is representing the characteristic impedance of the transmission line. And lastly, we have on the right hand side the actual load impedance. So here this is that load impedance. So here how many different types of impedances we observe in this circuit? Basically there are three different types of impedances we normally encounter in a particular circuit. Okay, so here these impedances are the generator impedance, the load impedance, and the characteristic impedance of the transmission line which is connecting to generator and load. Okay, now let us say the length of this transmission line is small l. Okay, so what will happen here, the situation is, if we do not have the values, now we will discuss a cases in which we will get mismatches between load and generator side. Okay, so here we are going to discuss a phenomena of mismatching between generator and load impedances, and because of which the reflection tend to happen. Okay, and in order to avoid that reflection we need to design a matching circuit. So that's why we are over here to illustrate this particular phenomena, why the impedance matching circuits are used. Okay, so the impedance matching circuits are used in order to minimize or to entirely remove the reflection. The reflection may happen because of mismatch between the impedances. So here the actual impedances are three different impedances: the load impedance, the generator impedance, and the characteristic impedance of the transmission line itself. Okay, so the cases could be three distinct cases. So the first case over here is the generator impedance Zg is not equal to characteristic impedance of a transmission line. Okay, so whenever there is a mismatch in the impedance, reflection tend to happen. Okay, so for example over here, if Zg generator impedance is not equal to characteristic impedance of the transmission line, then there has to be a reflection on the generator side over here. Okay, and that reflection we denote by this gamma, capital gamma letter. Okay, so the reflection will take place on the generator side. Similarly, if the load impedance, second case over here, if the load impedance is not exactly equal to characteristic impedance of the transmission line, so at that time also reflection will happen. Now that reflection we denote with gamma 1. So please remember, gamma is a reflection on generator side. Here I will write, it is a reflection on generator side. And similarly, whenever the second condition happens, that is the load impedance is not equal to characteristic impedance of a transmission line, then there is again another type of a reflection take place, that is a gamma 1. Okay, so that is a happening at the load side. So these reflection coefficient will become non-zero. Okay, and the third case where both mismatch can occur. So that means the generator is also not matched with the characteristic impedance of a transmission line in this case, and the load impedance is also not matched with the characteristic impedance of the transmission line. So there are three different cases. First case is the generator is not matched with the transmission line. Second case, the load impedance is not matched with the transmission line. And the third case could be both the impedances, that is the generator as well as load, they are not matched with the characteristic impedance of the transmission line. Okay, so here we have indicated when the load is mismatched with Z0, we get a reflection gamma 1. Okay, that is denoted over here. Similarly, when the generator impedance is not matched with Z0, we will get a reflection coefficient gamma. So let us represent gamma and gamma 1, these two different types of reflection coefficient in terms of impedances. So from your earlier understanding in RF circuit design subject, the reflection coefficient can be conveniently represented in terms of ratios of impedances, and the same is given over here. So how the gamma 1 is given? So the gamma 1, that is the reflection because of load impedance mismatch with characteristic impedance of transmission line. It is given by this particular equation over here. So I will change the color so that we can understand, or otherwise I will make use of a highlighter. Okay, so this equation over here is going to give us the reflection coefficient that is happening at the load side, that is gamma 1, ZL minus Z0 divided by ZL plus Z0. Now on the similar basis, we can write the reflection that can take place because of the mismatch between the generator impedance and the characteristic impedance of a transmission line. So similarly, we can write gamma is equal to Z0 minus Zg divided by Z0 plus Zg. So this is already covered to you in your third year engineering. Okay, so in RF circuit. Okay, so we will define one more important parameter. Okay, so though this parameter you already know, that we call it as a standing wave ratio. Okay, so if we know the reflection coefficient, we can calculate the standing wave ratio. So a basic equation to calculate the standing wave ratio, or in short it is called as a VSWR, in terms of reflection coefficient is given by this equation. So standing wave ratio is simply a ratio of 1 plus gamma divided by 1 minus gamma. Okay, so if reflection becomes 0, when the reflection will become 0? When there is a no mismatch. Okay, so please remember, it is very important, whenever there is a mismatch, the value of a gamma will be non-zero. Okay, so always we want to make the value of gamma to be 0. So what the value gamma is equal to 0 indicate? What this value is going to indicate? So when I write gamma is equal to 0, what that indicate? This indicates that no reflection condition. No reflection condition. So this condition is a desired condition, right? And we want to achieve this condition in every microwave circuit. There should not be any reflection of the wave. Okay, so that means when the wave is incident, it should only travel in a forward direction and nothing should get reflected back. So at that time, reflection coefficient will become 0. So if we replace the value of reflection coefficient into the equation of standing wave ratio, so the value of standing wave ratio we will get 1. So please remember, when the standing wave ratio becomes 1, it is indicative that reflection is 0. And reflection is 0, what that indicate? It indicates matched condition. Okay, it indicates matched condition. Matched condition of whom? It may represent a matched condition between Zg is equal to Z0, or it represents matched condition between ZL is equal to Z0, or both of them. Okay, so please remember here, in order to make gamma is equal to 0, so what we will be doing is we will be inserting a extra network in the microwave circuit. Now that extra network or the extra circuit, we are going to call it as a impedance matching network. Okay, so the impedance matching network will always ensure that the impedances are matched on the both the ends of the transmission line, and that's why they will ensure that gamma is going to become a 0, which will give us standing wave ratio is equal to 1, and it ensures that whatever we feed it up, that fed signal will only travel in the forward direction, that is the incident wave, and nothing will get reflected back. Okay, so we can calculate the power in this particular condition, taking into the account the complex load impedance which is connected at the load side. Okay, and similarly the generator at the source, it is also going to have its own impedance. So the equation of the power that will get transferred from the generator side to the load side is given with this equation. Okay, so it is a 1 by 2 generator voltage square divided by multiplied by R in divided by this whole term. Okay, so here we consider input impedance Z in. Please remember this input impedance Z in is indicated over here. The input impedance Z in is the impedance observed by looking into the transmission line towards the load side. Okay, so this impedance, how it is given? It is given in terms of real part and imaginary part. And similarly we have the generator impedance Zg, which is again represented into real and imaginary part. Okay, so by the basic theory of a transmission line theory, we know that the input impedance is given by this particular equation. Okay, so Zin in terms of characteristic impedance of a transmission line, Zin is equal to Z0 times ZL plus J times Z0 tan beta L divided by Z0 plus J ZL tan beta L. Okay, so what is L over here? The L is nothing but the length of the transmission line. Okay, so this equation you already know in your third year. Okay, and what is beta? Beta is a phase constant and it is written as 2 pi divided by lambda. Okay, so let us discuss further. When the load is matched, okay, the load is matched with whom? The load is represented by ZL. It is matched with a transmission line characteristic impedance Z0. So when it matches, gamma 1 becomes 0, right? Gamma 1 becomes 0. So gamma 1 is already given as ZL minus Z0 divided by ZL plus Z0. So it will become 0, and the same power equation can be reduced to equation number 2. Okay, so first condition we observe over here that if the load is matched with the characteristic impedance of a transmission line, provided the generator is fixed. Please remember, provided the generator is fixed. Okay, so at that time the power equation that will get delivered to the load will reduce to equation number 2. Okay, and second condition, when the generator is matched to the transmission line, provided load is fixed. Load is fixed. So second condition we will see. So the reverse of the first condition. Okay, so the second condition is we will match the generator impedance with the characteristic impedance of the transmission line. This condition. Okay, provided we assume that the load is already fixed. Okay, so at that time gamma will become 0. Okay, so when we substitute gamma is equal to 0, the power equation which is originally given with this equation will get reduced to equation number 3. Okay, and these two cases, the case number 1 where we are going to match the load impedance with the characteristic impedance of the transmission line, and in second case we match the generator impedance Zg with the characteristic impedance of a transmission line. Okay, now the third situation in which we are going to match both. Okay, so the first, simultaneous matching. So the third case is very important, and this case is of special concern for us. The third case, the aim is to match the generator impedance with characteristic impedance of the transmission line, as well as, and please remember, we need two conditions. We also want to match the load impedance with the characteristic impedance of a transmission line. So that means we want to match generator with transmission line, and we also want to match the load with a transmission line. So if this is the particular case, this particular case we call it as a conjugate matching, or we also call it as sometimes as a simultaneous matching, because here we need to match two quantities with the transmission line impedance. One is the generator impedance and another is the load impedance. Okay, so at that time what we do is, we know that the input impedance is represented as Zin is equal to real time plus some imaginary part. Okay, so the equation of the power that we know from equation over here, what we do is we will take the derivative of this particular power with respect to real part of the input impedance. So what we do is, from equation number 1 over there, we will take the derivative of that power with respect to real part of the input impedance, and then we equate it to 0. Okay, and then after simplification we will get certain equation. So that equation is represented by equation number 4. And similarly, this power equation over here, the original power equation, let us call this as equation number 1. We want to call it as equation number 1, please remember. Okay, so this is equation number 1. Take the derivative of this equation number 1 with respect to imaginary part of the input impedance and equate it to 0. Okay, so whenever we take the derivation of the power, if we take the derivative of the power and when we equate the derivative of the power to 0, that means we are finding a condition to maximize the power. Please remember. So when we take the derivative of the power and when we equate that derivative to 0, the aim is to find a condition in order to transfer the maximum power. So what we are doing, we are taking the derivative of original power with respect to real part and equating it to 0, and similarly we are taking the derivative of the same power but with respect to imaginary part and again equating it to the 0. Now in doing so, we will get two equations. Those are represented by equation number 4 and equation number 5. Okay, so equation number 4 and equation number 5, what we do is we simultaneously solve them for finding the values of real value of impedance and imaginary value of impedance. Okay, so finally what we get is the real value of impedance. We will get R in is equal to product of real value of generator impedance multiplied by imaginary value of input impedance, or it is also written as negative value of imaginary value of the load impedance as generator impedance multiplied by input impedance Zin. Okay, and in short it is written as complex conjugate. So here what we can write is input impedance if it is complex conjugate of generator impedance. So this condition we are going to get. So that's why this particular matching, simultaneous matching condition sometimes is also called as a complex conjugate matching. Okay, so please remember, if you solve equation number 4 and equation number 5 simultaneously, you will get this particular condition where the input impedance of the network is equal to complex conjugate of generator impedance, where R in is going to stand for real part of the input impedance of the transmission line equal to complex conjugate part of the generator impedance. And this is why this particular third special case of matching circuit we call it as a complex conjugate matching. Okay, so please remember, these are the different ways in which we are going to study the impedance matching. Okay, so the impedance mismatch may be happening at the load side, the impedance mismatch may be happening at the generator side, or in third case it could be happening on the both sides, that is on generator side and load side. Okay, so here we considered what is the basic purpose to design the impedance matching circuit. Okay, so again I will revise over here. The main aim to design the impedance matching circuit is to ensure that there will not be any reflection. Okay, why reflection is happening? The reflection is happening because of mismatch in the impedance. This mismatch could be at the load side, or it could be at the generator side, or it could be happening on the both side. Okay, so the three different cases we discussed: how to deal with a mismatch that is happening at the generator side. Then secondly, in the second condition, we dealt with how to remove the mismatch at the generator side. And the third special case we studied, whenever there is a mismatch on the both side, a complex conjugate technique we can make use of, which will help us to remove the reflection. Okay, so here we have formed a theoretical background in order to understand why there is a need to make use of impedance matching circuit. Okay, so I hope you understood the theory over here that we just right now explained in order to illustrate you what is the use of impedance matching circuit. Okay, so this is the foundation theory, and here we discussed the generator and load mismatches, and we have demonstrated that if we make use of a matching circuit, then these matching circuit will ensure that the reflection is going to become a zero and the impedances are going to get matched. Okay, so here I will stop, and in our next session or in next lecture, what we start with directly the foundation of impedance matching circuit. So here I will stop, and thank you very much.